Okay. Oh, let me fix this really quick. Okay, so the plan for today is to wrap up our last kind of minor expository topic on correlation and regression, chapter 10. Um, so this is a huge topic that could, that could be a whole semester course at the very least. Um, but we're just kind of scratching the surface. This way, if you see this idea come up in the future, you at least have a jumping off point, at least some idea of how correlation and regression works. So that's the goal for today. Just a reminder that chapter 11 and 12 have been supplemental videos have been posted and available for that for the past week or so. And of course, we are in the midst of final exam week. So same comments as before. Make sure to note that it's due Friday the 9th, so this coming Friday, and make sure that you plan to take it, I would say, on or before actually Wednesday night. I think I had to fix that last time too. I prepped my slides for these last couple of weeks well in advance, but plan to take it on or before Wednesday night. And that way, if anything does go wrong, you have 2 full days to work something out, get in touch with me, whatever, and get that sorted out. The quote of the day today is from Charlie Munger of Berkshire Hathaway fame. So he and Warren Buffett, did run the uh, the investment firm Berkshire Hathaway. Charlie passed away maybe a year and a half ago or so, and actually just over the weekend, I had this quote from my one class last Thursday, and then for the 2 classes today. And Warren Buffett actually just stepped down as CEO, or I guess announced his plan to step down as CEO of Berkshire Hathaway. So another big, big, blow to them, I suppose. But Charlie Munger is kind of known for having, you know, if you watch their annual shareholder meetings, somebody will ask a question, and Warren will give a very well thought out, measured, careful answer, and then Charlie will just give, a one line like sarcastic answer or something like that. Charlie did a presentation. I think it might have been like a speech at a business school or something like that, but it's called Psychology of Human Misjudgment. You can find it on YouTube. It's actually a really good speech. It's about an hour long. It talks about a lot of things, not necessarily related to finance, just how people make decisions in general. And if you're dealing with people making decisions, this is good stuff to think about. But at one point, he gives the quip, "It's better to add a sigma than change a theory." And some of the background to this is there is this idea in finance called the efficient markets hypothesis that, roughly speaking, says you can't beat the market on average over a long period of time. And Berkshire Hathaway at that time, the time that this guy was, getting a Nobel Prize for this and all that, Berkshire Hathaway was beating the market on average over a long period of time. And people would ask this efficient markets hypothesis Nobel laureate, well, how do you explain Berkshire Hathaway? And he would say, oh, it's a 2 sigma event, right? I mean, there's lots of companies out there over lots of time spans. Just by chance, one of them is going to beat the market for a little while, over a short period of time, or even an intermediate period of time, just by chance. And then, a couple more years go by, and Berkshire's still beating the market for those years. And he says, oh, it's a 3 sigma event. And so this is where Charlie says, he finally got up to 6 sigmas. And we know that a 2 sigma event is like 1 in 20, a 3 sigma event, maybe 1 in 300. There's certainly 300 companies out there, so no big deal to say, oh, it's a 3 sigma event. Yeah, that's probably going to happen. But 6 sigmas, 4 standard deviation event is like 1 in 30 or 40,000. I don't even know what a 6 sigma event is. It's extraordinarily unlikely. So Charlie's quip here is better to add a sigma than change a theory, right? This guy had his whole career staked on the efficient market hypothesis being correct. And you can either dig in your heels and insist your theory is right, and this is just an outlier event, uh, And that's easier to do than to say, okay, maybe I was wrong, and maybe there is actually a way to beat the market on average over a long period of time. Um, right? It's very much like our hypothesis testing idea. This guy, the Nobel laureate guy, is digging in his heels despite overwhelming evidence that suggests that his theory isn't entirely correct. Um, and according to Charlie, the guy went into money management, like opened up a firm and sank like a stone, as he as he said. So um, it is somewhat ironic that somebody who proclaims the efficient market hypothesis would set up a money management firm whose job is to beat the market on average over a long period of time when they say that's impossible to do. So, and charge people a large commission to do so. Okay, so that is so the plan for today is to talk about chapter 10, correlation and regression. Okay, so let's ask ourselves, what is correlation regression? What's the goal here? Well, one thing that we want to think about is correlation regression relates to two variables. So pretty much everything that we've talked about up to this point really only relates to one variable we're studying, right? We might want to develop a confidence interval or evaluate a hypothesis test for the mean of one variable. Or we might want to get, figure out the mean of a sample for one variable coming from one variable. So pretty much everything we've done up to this point is just one variable. But now we're taking a look at the relationship between multiple variables, between two variables, in this case, X and Y. So what does our data look like? Well, our data looks like we have data point, say, indexed by I, 1, 2, 3, down to n. We have n data points. But before we might say, okay, I'm looking at heights of people in Pittsburgh. Well, person one has this height, person two has this height. So I might have X and some data from my random variable. But now I have two variables, X and Y. And it's very important that these data are coupled like this, right? So I have data point one is this value for X and this value for Y. In other words, I might be thinking of, instead of just measuring someone's height, I maybe measure somebody's height and that same person's weight. And those two are inherently coupled, right? Those both belong to that same person. Person one has this height and this weight. Person two has a different height and a different weight, but person two's height and weight are coupled together. I can develop a graphical representation of this. So maybe I have the X and Y variables represented. And I can look at, say, point one as being like X comma Y, being like an ordered pair. So maybe this is data point one there at that value of X and that value of Y. Maybe data point two is here, three here, and so on. So maybe these are my n data points plotted on a scatter plot. So I can visualize this data using a scatter plot. That's my graphical representation. And I might look at this and I might want to ask, well, do I think that there is a relationship between these variables? In other words, if maybe X is height and Y is weight, do I think there's a relationship between, say, a person's height and weight? And it does kind of seem that way. It does seem that if we take, say, roughly maybe the middle-ish of this data set, basically X bar comma Y bar, and I kind of draw a set of coordinate axes through there, it does seem like there is more data in the top right and bottom left in the first and third quadrants than in the other two quadrants. In other words, it does seem like there is a positive relationship between these two variables. What do I mean by that? I mean that, well, it seems to suggest, this data seems to suggest that if I observe a person who has a fairly high height, a fairly tall person who has a fairly high value for X, then I would kind of suspect that they will also have a fairly high value for Y, that they'll have a fairly high weight, and vice versa. If I observed a person and saw that they have a low height, then I'd expect them to have a low weight. So that's a positive relationship where the variables are kind of somehow in concordance like that. Okay, so let's dig in a little into this in a little more detail. So we have the idea of a correlation coefficient to start off with. So here we have the correlation coefficient is represented by either rho. It looks like a little p there, but that's the Greek letter R, the Greek R. So it looks like this. That's the letter rho. That would be our population correlation coefficient, or the Roman letter R being our sample correlation coefficient. Now, one thing that we notice is by definition, our correlation coefficient is between -1 and +1 inclusive. So the same way that, like, say, a variance cannot be less than 0 by the way that it's calculated, in the same manner, a correlation coefficient cannot be below -1 or above +1. It has to be between -1 and 1 inclusive. Now, what's the goal of the correlation coefficient? It's to describe the degree and the nature of the linear relationship between the two variables. And there are two characteristics in play here. The magnitude, in other words, the absolute value, is it close to 0 in absolute value or close to 1 in absolute value? Or in other words, is the correlation coefficient itself close to 0, or is it close to either plus or minus 1? And also the sign, is it positive or is it negative? So respectively, this represents the degree of the linear relationship. In other words, the amount of the linear relationship. Is there evident a strong linear relationship, or is there a lack of evidence of a linear relationship? And the nature, is it positive or negative? We saw a fairly strong degree of linear relationship up here. This seemed to be a relationship between X and Y. And it was positive because higher values for one were associated with higher values for the other and vice versa, rather than say higher values for X being associated with lower values for Y and lower values for X being associated with higher values for Y, where they would be kind of opposites like that. That would be a negative relationship. Okay, so the magnitude is what indicates the degree of the relationship. Is there strong evidence of a linear relationship or weak evidence or no evidence? And the nature of that relationship if it exists. So the magnitude, or in other words, the absolute value, if the magnitude is near 1, in other words, if the correlation coefficient itself is either near +1 or near -1. So if the magnitude is near 1, what does that mean? That means, and as an aside, I'm not going to be super careful with whether I'm using the population parameter or the sample statistic here. Not going to, yeah, I might go back and forth between them, but I'm not being super careful here. So the magnitude can be near 1 again if the correlation coefficient itself is either near -1 or near +1. That indicates a high degree of linear relationship. In other words, something like up here, where I see that there is a nice pattern where I can associate high values of X with high values of Y and low values of X with low values of Y. That's as opposed to maybe something like this, right? If I know something about X, if I'm say if I observe an individual and see that they have a high value for X, well, that doesn't really restrict their possibilities for Y at all. There is essentially no relationship between X and Y. These are something like independent variables. Whereas here, if I see that I have a high value for X, my possibilities for Y are significantly constrained. We're not going to be, it's not likely that we're going to be down here anymore. My values for Y are probably going to be somewhat high as well. So magnitude near one gives us strong evidence of a linear relationship existing. Whereas near zero, there's a low degree or low evidence of a linear relationship, right? We're looking at something like over here. Now, it is possible that we have, in essence, no relationship whatsoever between X and Y, but I've been glossing over this point that we're looking to study the linear relationship. We could have a situation where we have a very clear relationship like this. Maybe this is something like speed versus mileage, miles per gallon. If you're going really slow, your car is just burning fuel to just keep running and not getting you very far. But if you're going very fast, you're combating a lot of rolling resistance from the tires and air resistance from the wind. So in both cases, you take a hit to efficiency. And here, if I restrict myself to say the higher end of speeds, I still kind of run the gamut of different miles per gallons. So there's a relationship here, but it's not really linear, right? It's inherently somehow like non-linear. We'll talk a little more about that in a couple minutes. But a magnitude near zero, which means that rho is near zero, maybe a little bit positive or a little bit negative, but near zero, either way, suggests a low degree of linear relationship. Now, if we want to describe the nature of a relationship, we should have a relationship existing in the first place, right? So we can say now if something like the magnitude is near one, and we could ask, well, how close to one should it be for us to say that it's near one? And that's probably going to be dependent on the field, the types of correlations you tend to get in a certain field, dependent on the person's, goals and what other, competing models they have to work with and so on. But if the magnitude is near enough one that we say, okay, we think there is evidence of a linear relationship, then what can we say? Then we can describe the relationship. If the sign is positive, rho is near plus one. Remember, magnitude near one means either rho is near negative one or rho is near positive one. So if we get a magnitude near one by getting a rho near positive one, we say the two variables have a positive relationship. In other words, large values of X tend to be associated with large values of Y and vice versa. Right? That was the situation we had up here. That if I observe a person and I note that they are taller than typical, I would expect that they probably weigh more than typical. And vice versa. If I observe a person and I see that they are shorter than typical, I'd expect they probably weigh less than typical. On the other hand, I could have a correlation near -1 that would give a magnitude near +1. It would give an absolute value near a +1. In this case, the nature is negative. And we have this kind of inverse or opposite relationship that large values of x tend to be associated with small values of y and vice versa. So if I observe an individual and I see that their value of x is larger than typical, I might expect their value of y to be smaller than typical and vice versa. So positive scatter plot or positive relation in a scatter plot will look something like this. A negative relation will look something like that. Both of these would be a correlation near 1 in magnitude. This one being rho near +1, this one being rho near -1. And then rho near 0 could be essentially an absence of a relationship like this here. If I know something about x, that doesn't really inform anything about y and vice versa. Essentially, these two variables look like they're independent. Or it could be a situation where I have a relationship, but it's just very nonlinear. Or kind of if I'm unrestricted in x, this is the gamut of y values that I might expect to see. But if I restrict x to say these larger numbers, I have the same gamut of y values. I haven't really gotten anywhere. So knowing something about x doesn't really tell me very much about y, and vice versa. If I kind of know something about y, if I know that y is, let's say, we'll do lower, if I know that maybe y is lower than typical, well, my x's could be here or here or here or here. I still kind of run the whole gamut of possible x's, right? So I can have something non-linear where knowing something about one variable doesn't tell me a whole lot about the other variable. Okay. Give me a second to pause my screen here. I'm also going to, my windows are not cooperating. Let me just stop my share for a second. I think my OneNote froze up. Okay, there we go. I'm going to pop a couple of Excel files in chat for you. If I can get this to work. Put the chat all the way on the right side of my screen and my files are on the left side, so see if I can. Can I copy and paste? Well, let me do that. Okay, good. All right, so I popped 3 Excel files in chat for you. And there's one called correlation demo, file number 1. And there's another file called correlation worksheet. So that's what we're going to work on for the next few minutes here. Let me get those started up on my end. All right, let me switch my screen over and then, all right, we are all ready to go now. So the first one here, correlation demo. Actually, sorry, let me pull up the other one as well. Might as well get that one started up too. Zoom is not being super cooperative with, where it's putting the toolbar relative to the window minimizing and maximizing buttons. So having to shuffle things around here quite a bit. Okay. There we go. I think we are all good now. So let's start with number one here, the correlation demo. And here I have examples from the stock market. This is from back in 2013. So some of the examples I'm using are from older data, and then some of them from newer data. So I have listed here on a given date, what is the price of two different assets? One is Google stock price, and one is something that's called Spider Gold shares. Essentially, this is like if you want to invest in gold, but don't want to like have gold that you have to do something with, like either put in a bank safe deposit box or like put in a safe in your house or something, you can just buy this, what amounts to something like a stock in basically a company. And what that company does is the company just buys gold and puts it in their vault. And then like by owning part of that company, you own a share of that gold. So it's a way to invest in gold without having the carrying costs of actually taking possession of the actual bullion yourself. But we can see on say April 15th, 2013, a Spider Gold share was valued at 135.47, and a share of Google stock was valued at 799.87. Now, this isn't necessarily saying that one company is more valuable than the other. Companies can have different numbers of shares of stock. So the market capitalization is number of shares of stock times price, and that kind of gives you a rough idea of what the company is worth. Companies can also have other kinds of assets too, but or other kinds of investors and so on, but that gives you kind of an idea. And we can see that on a different date, these two assets had a slightly different value. So we have paired data here. For this date, these two numbers inherently go together. For this date, these two numbers inherently go together, and so on. If we look at a scatter plot, we see that it looks like this. And honestly, it just kind of looks like a blob. Right, I see gold basically going from 150 to 175 or so, just kind of smeared about. And Google going from about 550 to 850, again, just kind of smeared about. If I screen cap this and bring it over here, let's forget about these two outlier points. These are kind of strange points that seem out in the middle of nowhere. But if we forget about those and I look at like the middle of the data, it might be something like here. And I draw a couple of coordinate axes through there, vertical and horizontal axes. And maybe I look and see, do I see more data in quadrants 1 and 3 than in 2 and 4? Or do I see more data in quadrants 2 and 4 than 1 and 3? Or neither of those cases? I think neither of those cases, right? I see about the same amount of data points showing up in quadrants 1, 2, 3, and 4. So like if I knew that gold, if I looked at the market today and saw that Spider Gold shares were a bit high today, well, Google could be high, but it could be low. Or if I saw that Spider Gold shares were low today, Google could reasonably be high or low, right? I don't think that knowing something about one of these assets tells me very much about the other. In other words, I don't think that the magnitude of the correlation is going to be near 1. I think it's going to be near 0. And to have a magnitude near 0, the correlation itself has to be near 0. And we do see that. If we ask Excel to tell us what the correlation is for uh, these two data sets, so gold and Google over the span of a year or so, weekly data, well, it gives us a correlation of negative 0.01. 0.01 on the scale of basically 0 to 1 or 0 to 1.00. uh, that's about as close to zero as you're going to get. So I don't think that there is really any evidence at all of a linear relationship between Spider Gold shares and Google shares. What if I look at gold versus Microsoft? Again, similar thing. I look at the scatter plot. I don't see really any rhyme or reason to the scatter plot. And again, I see a correlation pretty close to zero. Now this one's 0.08 instead of 0.01, well, negative 0.08 instead of negative 0.01, but still that's quite close to zero. If I look at Google versus Microsoft, these are kind of in the same sector, right? They're both tech companies. So maybe they're competitors. Maybe when one does well, the other one does a little worse. Maybe they, since they're in the same sector, maybe when one does well, they might expect the other one to do a little better because maybe that sector is doing well as a whole. But I look at the data, I see a correlation. Now this correlation is negative 0.32. Now that's on a scale from 0 to 100. So it's about like a third of the way from 0 to 1. Sorry, 0 to 1.00. Like kind of something like 0% to 100%. The magnitude is 0.3 on a scale from 0 to 1. That's not super close to 0, but it's still a good bit closer to 0 than it is to 1. So I'm still looking at this and thinking, okay, there's probably not a really strong degree of relationship between these two variables. What about Google and Yahoo? We're getting a little closer together in the types of companies now. They're both search engines. Actually, I don't really know what Yahoo does today. They're still around, I think, but I'm not really sure what they do. But at least back in 2013, Yahoo wasn't, quite as unknown as it is today. But now we're getting somewhere. Now, number one, if I look at let me cut and paste this. Let me screen cap this. If I look at the scatter plot, I'm starting to see something interesting. Again, if I do my little trick of taking what feels like about the middle of the data, like the center of mass of the data, or like the average of Yahoo, and maybe the average of Google, something like that. Now I am starting to see that in quadrant one, there's a lot of data points, and in quadrant three, there's a lot of data points, and not so many data points in quadrants 2 and 4. It seems like there is a positive relationship here. In other words, it seems like if I know that Yahoo is high, if I open the Wall Street Journal, tomorrow morning and I see that Yahoo's share price is high, I might expect that Google's share price would be fairly high that day as well. Or if I saw that Yahoo was low, I might expect Google to be low that day as well. So I see a stronger nature of linear relationship. We see the correlation, the magnitude is about 0.8 on a scale from 0 to 1. That's getting pretty close to 1. And because I now have a fairly strong linear relationship, I have strong evidence of a relationship, I can describe that relationship. I would describe this as a positive linear relationship. Once I have a relationship, I can describe its nature. And because the correlation coefficient is positive, rather than being negative like these ones over here, since it's positive, now I can say that it has a positive nature. It has a relationship, evidence of a relationship, and in the positive direction. That higher values of one are associated with higher values of the other, and vice versa. And we could look at something like PIMCO and Microsoft. This is PIMCO's high equity bond fund. So these are high yield bonds. These are risky bonds where the companies maybe aren't in the best financial shape. And typically when the stock market does well, usually bonds do poorly. So usually you'd expect to see a negative relationship between kind of any bond asset and any stock asset. But interestingly, with high yield bonds, because the companies aren't in the best financial shape, if the stock market's doing poorly, that means the overall economics aren't doing so great. And that's when those companies are actually more likely to default on their bonds. So with these riskier bond issues, they move a little bit more like stocks than like your typical bonds. But we look at these variables. PIMCO is just the name of a company that runs mutual funds. So they have a big fund and they buy these high risk bond issues, and then people can buy shares of that. So PIMCO's bond fund versus Microsoft's share price, and we see a correlation of about positive 0.7 or so. Not quite as strong of a positive correlation as Google versus Yahoo. The picture doesn't look quite as pretty, but I think we can still see this general kind of positive trend that if our X value was fairly high, we'd expect our Y value to be fairly high as well. And if our X value was fairly low down here in the say 10 to 11 range, we'd expect our Y value to be fairly low as well, maybe in the 26 to 28 range. Now, how do we compute a correlation coefficient? Well, we're not going to do this by hand because the calculation is quite long and cumbersome, but Excel has it programmed in. It uses the CORREL function. So we just do equals CORREL of, and it says array 1 and array 2. So I need to give it two lists of numbers. So I give it PIMCO's data, comma, Microsoft's data. And I'm just clicking the first cell, scrolling down, and then holding shift and clicking the last cell to make it easier to enter it. So I don't have to click and drag, and then if I drag a little bit wrong, it gets messed up. But it is important that these two lists are the same size, of course, because Excel is expecting you to give it paired data. So it's going to take the first data point or the first value from the first list and the first value from the second list and kind of pair them together. Do that for the next values and the next values. If it gets down and like one of the lists ends and the other one doesn't end, it doesn't know what to do. So if I did like this, where I have lists of two different sizes, Excel is just not going to really know what to do. So I do need to make sure that I give it two lists that are the same size. And there is our correlation. So we can compute the correlation that way. We'll also see a bit of a quicker way to compute it later on when we talk about regression. Let's jump over to file 3 that's titled Regression Demo 24 Fall. And let's go over to this tab on the bottom that says CORREL chart. So correlation chart. And here we have for fall of 2024, well, for about 2 years or so, but ending in fall of 2024. We have for a bunch of different assets. These are Spider Gold shares that we're associated with. Well, these are like silver shares. They do the same thing, but with silver. Google stock price, Tesla stock price. I did this in fall 2024, so before all of the Tesla political stuff came about. So no political statements here about Tesla or anything like that. I don't want to redo all of this data. It was a lot of work. Amazon and PIMCO. So Amazon stock price, everybody knows what Amazon is, and PIMCO I already kind of mentioned, their high equity bond fund. And sometimes you'll see a correlation chart or a correlation matrix like this, where if we have maybe a bunch of different assets, here we have 6 different assets, maybe we're interested in knowing what are the correlations of each one with each other one. Now, of course, like if I look here, the correlation of the gold shares with the gold shares is, of course, 1. That's just the correlation of a variable with itself. Of course, that is perfectly that is a perfect linear relationship. Whenever gold goes up by $1, gold goes up by $1 as well. So, but if I look at, say, silver versus gold, I can see that either here or here. It's the same thing. Gold versus silver or silver versus gold is the same correlation. I see a correlation of 0.94. I would kind of expect that, right? These are both Bullion, they're both kind of safe havens. Whenever something's going a bit awry in the stock market, people will sometimes sell their stock and buy gold or silver. Um, so this doesn't surprise me that gold and silver are highly positively correlated. They have a high degree of linear relationship, 0.94 on a scale from 0 to 1. Not going to get much better than that. And they also have a positive nature, that the correlation coefficient itself is positive. I look at something like Google versus Tesla, a search engine slash tech company versus something like a car slash AI company, and their relationship isn't nearly as strong. 0.35 on a scale from 0 to 1 for the correlation coefficient, right? There's maybe some degree of relationship here, but it's quite small. Or if I look at, say, silver versus Tesla, are the people who are likely to invest in, say, bullion like silver, or the time periods where people are interested in investing in bullion, do they tend to be similar to the ones where people are investing in kind of a frontier type company that could crash and burn or could do great, like Tesla? Um, Maybe not so much. So we see a much lower correlation between these two as well, and same with like gold and Tesla. But actually, things like gold and Amazon or silver and Amazon are actually fairly highly correlated. I mean, Amazon is a big enough company, it's kind of a safe bet, right? Like Amazon's not going to go bankrupt tomorrow. And of course, something like Google and Amazon have a very high correlation. They're both very big companies. They're both kind of market leaders in their areas. And Amazon, I mean, Amazon's kind of a uh, they're kind of I can't think of the word, but they're kind of a department store type company, but not really. Amazon's actually really a tech company, kind of hiding behind the scenes, right? They're a tech and logistics company more than more than like a Walmart or something like that. Now, of course, they compete directly with Walmart, but their strength is in their technology and their logistical efficiency, their logistical network. And similarly with Google, they're kind of market leader, huge company. Amazon is also heavily diversified. I mean, we interact with Amazon as random everyday people by buying stuff from them, but they have things like Amazon Web Services that companies will like host all of their websites and all of that on Amazon servers. And that's a service they provide. So Amazon does all kinds of other things as well that, we don't really see all the time. Okay, so we can look at a matrix like this, a correlation matrix, and maybe we're interested in figuring out which stocks are or which assets are highly correlated and which ones are less highly correlated, right? Maybe I want to kind of hedge my bet a little bit. So maybe I'll buy maybe some Tesla stock and some Amazon stock because they have a fairly low correlation. And my thought is that, well, maybe if I do that, it diversifies me a little bit, right? If I buy a bunch of silver and or some silver and some gold, that's basically the same as buying a bunch of gold because the two assets are so closely linked. But if I buy, say, some Tesla and some Amazon, that's like having two different eggs in two baskets instead of two eggs in one basket. I'm diversified a little bit. If one of them, one of these companies crashes in a given month, the other one's probably not going to. So it gives a little more stability to my portfolio. Okay. Let's bring up spreadsheet number 2 now. Let me expand this just a touch. I know this is a little bit hard to see on my screen, but that's why I also popped the Excel files into the chat, so you can bring this up as well. This is file number 2, the correlation worksheet. And so bring this up, and I have 5 different scatter plots here. And these 5 correlations, A, B, C, D, E, go with these 5 scatter plots. So see if you can tell which correlation goes with which scatter plot. As a side note, it would not be fair for me to say, look at this, top left scatter plot and estimate the correlation coefficient to within 0.05. That's not a fair question. But if I say, these 5 scatter plots go with these 5 correlations. Can you match them up? This is a fair question. So take about a minute or so, try to figure out which of these 5 correlations goes with which of these 5 scatter plots. And if you need a little bit of a hint, note that there are 2 positive, there are 2 negative, and 1 that's 0. So you can kind of start by like splitting up the possibilities that way. Which plots should the positives go with, which plots should the negatives go with, and then decide between which 2 positives go with which of these 2 plots and which 2 negatives go with which of these 2 plots. So take about a minute, take a look at this problem, and we'll come back to it. Okay, let's take a look at this. So let me jump over here to OneNote. I'm just going to kind of copy and paste this over here, see if it will cooperate. Okay, it came over as a reasonable size. So, all right, so if we take a look at this, I see I have a 0 correlation. I have 2 positives and 2 negative correlations. Let me look through these 5 plots and try to see if I can tease out which ones I think have positive versus negative or 0 correlation. Well, if I look at top left, that's pretty clearly a negative correlation, right? If I imagine putting some coordinate axes through the middle here, I have a lot more data in, say, the second and fourth quadrants, where X and Y have opposite signs, than I have in the first and third quadrants where they have the same signs. This would suggest to me a negative relationship. Now, similarly, the bottom right, I think I would have a positive relationship there. The other 3 might be a little bit hard to tease out, but again, if I do this trick of putting coordinate axes in, I think that makes it easier to see. And then just take more or less the middle of the data set and draw these axes. On the bottom left, I see more data where X is small and Y is big, or where X is big and Y is small, than in the other quadrants. So I think that's kind of an opposite type of relationship. I think bottom left is also a negative correlation. Top center, I see most of my data is where when X is large, Y is large, or when X is small, Y is small. That seems like a positive relationship. And in bottom center, I see just kind of a smattering of data between the 4 quadrants. So I think I have positive here, negative here, and 0 there. Okay, so I think A, or 0 correlation, goes with my bottom center. Now I have 2 positive correlations, 0.96 and 0.80. I have to assign those to these 2 positive correlation graphs. Well, what does it mean to have a higher or closer to 1 positive correlation? It means that it's closer to, it's a tighter relationship. It's closer to a linear relationship. So if I look at this relationship versus this one, well, top center is more scattered about, and bottom right is more kind of tightly clustered together. There's a stronger linear relationship here. In other words, if I drew a line through this data, the points stay closer to that line than if I drew a line modeling this data. The points are more spread out on either side of that line. So I think my higher positive correlation is going to be bottom right. That's 0.96. That's going to be option B. And then my lower, but still substantial, still fairly high, but lower than 0.96 correlation is going to be top center. And then analogously, I have two negative correlations, negative 0.98, negative 0.74. Top left is going to be my negative 0.98 or option D. That's the correlation that's closer to -1. It's the tighter relationship between the points. And then E, still a decent negative relationship, but not quite as strong. Okay, let me close out this correlation worksheet. I don't think I need to save any changes. There we go. All right, so let's jump back over to just this OneNote file. There we go. And let's discuss our next topic. So let's discuss regression. What's the idea of a regression line? Well, our goal is to construct a linear model to model the relationship between X and Y. So again, let's take our height versus weight example, and we have maybe a scatter plot. Scatter plot displaying these paired data. Now I see that I have a correlation that's close to +1. In other words, there exists a linear relationship between these two variables. I can describe that linear relationship as positive, but that's a bit of a crude description of the linear relationship, right? It's not super helpful. I know that when one of the variables is higher than usual, I kind of expect the other one to be higher than usual and vice versa. That doesn't tell me very much or anything very precisely. Maybe what I want to do is to choose a model. Maybe I'll choose a model that is a line, say y equals alpha plus beta x. And then I can say, okay, if I, pick a person out of the crowd and I observe their height, and their height is height x, say right here, then I can give actually a very precise estimate of what I think their weight might be. My best guess at what their weight would be this number y that comes from this linear model. Or I would plug x in here. I'd be given the values alpha and beta. That's what determines the intercept and the slope of the line. And that would give me an estimate for y. If I've given their height, I can estimate their weight based on this. This can, of course, go the other way. If I'm given their weight, I could estimate their height as well. Okay, so what is my goal here? Well, I guess my sub goal, my overall goal is to construct a linear model, but what do I need to do in order to make that happen? I need to use the data to estimate alpha and beta, right? I could draw lots of lines as models for this data. I could draw a line like this, or a line like that, or a line like that. Most of them look like they're pretty garbage models. They don't do a good job of approximating the data. In other words, this line is quite far away from most of the data points. But the line that I drew here is quite close to most of the data points. The line I drew here would be a better model because it it stays closer to more of my data. So I want to use the data to estimate alpha and beta. Practically speaking, how do I do this? We'll talk maybe 30 seconds about this. Well, my 30 seconds will probably turn into 2 minutes, but anyway. So how do I do this practically? Well, I have some data points. I'll just draw a few data points. And I have a, say, potential linear model. And then I look at the deviations between the actual data and the linear model. In other words, my linear model for this value of x, let's say y equals, let's say alpha plus beta x, and that will be an estimate. So we'll call it y hat. But I have an actual data value for y associated with this value of x. So I have a model, an estimate, and an actual value based on the data. If these two tend to be far apart, my actuals and my estimates, this probably isn't a great model. If they tend to be close together, if my estimated values tend to be close to the actual values I got from the data, from the real world, then it's probably a better model. So I'm interested in y hat, or let's do it the other way, y minus y hat. But I do note that sometimes I can have a positive and sometimes a negative relationship there. If I just try to say, take the difference in each estimate for each data point and then add them together, I'm going to get a lot of cancellations. The positives are going to cancel with the negatives, and a model like this or like this is going to look pretty good because I'll have a lot of some high positive numbers and high negative numbers that'll cancel. What's our trick that we did before? Well, we square it. That makes everything positive, and then we add it together. We call this the sum of the squared errors, SSE. We take the estimate under a given model, subtract off we take the actual value, subtract off the estimate under a given model. We square that to make it positive, and then we add them all together for all the data points. Now, if I change my values for alpha and beta, if I change my slope and intercept, that gives me a different line, which gives me different errors, which changes this sum. And what I want to do is I want to choose the intercept and the slope. I want to choose the alpha and the beta, so to speak, for my model that minimizes this sum of squared errors. I want to choose the line, the slope and intercept, which uniquely determines the line, that minimizes the sum of the squared errors, that minimizes the squared distances between the lines, the line and the data points. Now, there is actually a closed form expression. I can say alpha should be this thing and beta should be that thing. If you write it in linear algebra format, it actually turns out to be a fairly nice formula. If you write it in not linear algebra format, it turns out to be a big mess of summation symbols and all kinds of things. But either one of those is really beyond the scope of this course. So we're going to ask Excel to do it for us. We're going to ask Excel, hey, you figure out what the alpha and beta are to give me the best model. Now, there are a couple of things I want to discuss here really quickly. The first is that this gives us a best in some sense, in the sense of minimizing the sum of the squared errors model. Is the best model a good model? Right? Like if I went out and raced, Eliud Kipchoge in a marathon on my best day, would I beat him? Would I even do well? Well, absolutely not, right? My best performance is not a good marathon performance. It's possible that the best model is a good model. I mean, this looks like a very good model. It's the best model and a good model. But if I if I ran this program on something like this here, where there's really no linear relationship, it's going to give me some kind of model. It's going to say, this is the best I can do. Is that a good model? Does it seem to do a good job of representing this data? Well, no, this is a terrible model. It's the best we can do, but it's still terrible. That's the first thing we need to understand, is that just because you find the best model with this process, which Excel will just crank out for you, it doesn't mean that it's a good model. And that's one of the big pitfalls here is people will get a regression model. They'll say, hey, here's my model. It's the line of best fit. Isn't that great? And then move forward before they even do the checks to see, okay, is this actually a good model? Is this a model I want to use? It's the best we can do, but it might be terrible. The second question is, well, we're really restricting ourselves here by using a linear model. I mean, why in the world would I expect that some complex process, some complex relationship between two variables ought to be linear? There's a quote that I cannot find the source for, but it goes something like dividing the world into linear versus nonlinear phenomena is like dividing all objects in the world into bananas and not bananas. In other words, like essentially everything in the world is nonlinear. So it seems kind of silly to use a linear model to model things in the real world when we're essentially certain that the relationship is not linear. We're inherently using the wrong model. But there's a big caveat here. My favorite grad school professor, Professor Layton, loved to say the world is locally linear, and linear algebra is where the rubber meets the road. It's what makes, applied math really run. The world is locally linear. So what does that mean? Well, if you've had exposure to calculus, this will be quite obvious. If you haven't, that's fine. Hopefully I will kind of convince you of this. We can have a very non-linear function. We can have a function like a sinusoid or something like that that doesn't look like a line at all. Thing is, if I zoom in on it, if I zoom in on a particular point of interest, well, a straight line is not going to do a good job of approximating this function at all over a very wide range, but over a very small range. As long as my function is kind of continuous and like smooth, it's not like pointy or jaggedy or anything like that. It doesn't jump around, doesn't have jump discontinuities. If I zoom in a little bit, if I look locally, if I look at a certain area, then actually a linear model typically does a pretty good job, right? Even if I look back up here at my miles per gallon example, I mean, no straight line is going to do a good job of modeling all of this data. None of them are good models. But could I kind of split this in half and have a linear model that does a good job on the left side and a linear model that does a good job on the right side, two different linear models? Yeah, I think I could. So there's, oh, um, so this is essentially the idea. We use a linear model for something like three reasons. One is the world is locally linear. If we zoom in on a nonlinear function, it looks like a linear function. Two, we can write essentially any nonlinear function as a linear part plus some other stuff, plus x something times x squared, plus something times x cubed, and so on. And often these so-called higher order terms, these nonlinear terms, don't have that much effect. That's often the case, not always, but and that's of course subject to certain constraints and so on, and as being local and that kind of thing. But this is also algebraically, it's graphically maybe a sensible thing to do, but it's also algebraically a sensible thing to do. That if I have a very nonlinear function like sine x or something like that, I can write it as like this infinitely long polynomial, and then just take maybe the first couple of terms, the dominant terms. And the third important thing is that linear functions are simple. So I'm sacrificing a bit of accuracy that I'm not dealing with the full uh, nonlinear phenomenon. But what I'm getting out of it is hopefully more than compensating for that. I'm losing a little bit of accuracy, but I'm getting a much simpler model to deal with that's much more understandable, where I can interpret the results. As a little side note, you know, with AI coming about, you might kind of roughly think of the way that we answer difficult questions in two regimes. I almost think of it as like the Plato thought process versus the Aristotle thought process. So one way could be like, Newtonian mechanics. Like I wonder how, when I roll this ball down this hill, how it's going to roll. And I dig deep into the foundations of physics, and I come up with like F equals ma. I come up with a model that explains this ball rolling down this hill, and that model actually might explain other things as well that aren't related to this. Or maybe I just take 10,000 balls rolling down 10,000 different hills, time them all, and I just like by brute force, just by like whacking the problem with a sledgehammer, putting a lot of effort and energy into it, I can just come up with like basically a lookup table for if I roll this ball down this hill, how's it going to roll? And I can just say this is the answer. The latter requires a lot less thought and maybe time. Um, so if I try to develop an underlying model, I have a deeper understanding of the process and maybe can generalize it better, but it probably takes me a lot more time and thinking and effort and so on to generate that model. If I can run an experiment hundreds of thousands of times really quickly, say on a computer, that's maybe in a sense what AI does, then I can get an answer much more quickly, but it's less generalizable and it's less easy for me to interpret and understand, right? So with a linear function, I have something that's simple for me to interpret and understand the results of, and I can make predictions that hopefully are reasonably correct. If I just want to make predictions, maybe I use something like AI, but if I want to understand the results, then I want something like a model. Okay, so as I said, we're trading off accuracy for simplicity. And just like we've seen through the whole course, that really these alpha and beta are related to the model we would get if we were dealing with the population of data points. And A and B is what we call it when we're dealing with sample data, right? If I have the population of all Pittsburghers that I'm interested in, if I have everybody's height and weight, and I do this process to get the regression line, I would call those alpha and beta. And if I have my population of Pittsburghers that I'm interested in, but I have a sample of size 100 and I have their 100 heights and weights, and I do this process, I would call the results A and B for the intercept and slope. All right, so that is our method. Choose our intercept and our slope, choose the line so that we minimize the sum of squared errors. And as I mentioned before, it's the line of best fit, but is it a good fit? That's not necessarily so obvious. Okay, I think, yeah, that was what I had to say for right now. Let's take a look at back over at Excel. All right, so let's look at the regression demo spreadsheet. So this is spreadsheet 3, where we had the correlation chart to start with. Now let's look at just silver versus Tesla. Again, sorry, I did these all before Tesla got all crazy in the news and all that. So let's look at silver versus Tesla. So this is silver shares. This is that company that basically just buys silver, puts it in their vaults, and sells shares, so you can own silver through a company without having to actually take possession of the asset itself. And this is Tesla's stock price. And again, this is data from a couple years in 2022 to 2024. If I draw a scatter plot, this is what the scatter plot looks like. If I look at a correlation coefficient, I see it's about 0.2. So not a very strong linear relationship between silver and Tesla. If I have a low correlation number, if I have a low magnitude of correlation indicating that there's really weak evidence of there being a linear relationship between the two variables, do I think that if I do a linear model modeling the relationship between these two variables, it's going to be very good? Probably not. If I'm saying that there's a low degree of linear relationship between the variables, a linear model probably is not a good model to use for that relationship. If I jump over to something like Google versus Tesla, a little bit higher correlation, 0.35 on a scale from 0 to 1 in magnitude, a little more of a degree of linear relationship, but still not very high. I expect my model, a linear model for this, to be maybe a little better, but probably still not great. If I look at, say, Google and PIMCO, I can even see, looking at the picture, if I were to draw a line here, I could probably draw a line that would be pretty close to most of the data points. And with a correlation coefficient of 0.78, I would expect my model to do a pretty good job of describing this relationship. I think there's a high degree of linear relationship between these two variables. Therefore, if I use a linear model to explain that relationship, I'd expect it to do a decent job. And then something like, say, Google and Amazon, again, looking at this picture, I think I could draw a line here that stays very close to almost all the data points. And with the correlation of 0.95, there's a very strong degree of linear relationship between the two. I think if I use a linear model to model this relationship, it should probably do an excellent job. Okay, how do we figure out what the linear model ought to be? Well, basically, we ask Excel to do it for us. We ask Excel, what choices of slope and intercept should I use? It'll run the calculation, and it'll give us something like this. And this is what I see here, these coefficients. In other words, what I'm saying is that we're modeling Tesla's stock price as, well, our intercept is 139.7. Let's just call it 140 plus 3.13 times the Spider Silver shares price. So this is our estimate. In other words, if I knew the silver shares were trading at, say, 10, then my estimate would be Tesla is about 140 plus 3.13 times 10, or 140 plus 31.3, 171.3 would be my estimate for Tesla's stock price if the silver shares were 10, or were trading at $10. If the silver shares were trading at $20, then my estimate for Tesla, I'd plug in 20 and figure out what this is, somewhere in the ballpark of, 202 or something like that. It's important to realize this is an estimate. I'm not saying that, like, if silver is 10, Tesla has to be 171. This is just a model. The real world is going to do what the real world is going to do. I'm trying to understand it and explain it a bit. So I might be saying to myself in my portfolio, okay, if I'm concerned about silver going down to 10, these silver shares that I have in my portfolio going down to 10, well, if that happened, what would I expect maybe I have some shares of Tesla in my portfolio. What would I expect to happen to those shares? And, if this happened, then am I concerned with that? Again, this has probably changed quite a bit because, of all the craziness with Tesla these past couple months. But let's just imagine we're talking about this in fall of 24 when this data was pulled from. So I see that I have a model of best fit. Now, one thing that I can do is I can list my silver and Tesla actual data, and then I can list my Tesla estimate. Right here are my intercept and slope. I just copied those over from the previous slide. It's 139.7 and 3.13. That's just these here. My estimate for Tesla's value is 139.7 or cell I22. Oh, here it is, I22, plus this 3.13 cell I23 multiplied by the silver share price. So when silver is 27.92, this data point says that in reality, Tesla on that day, whatever, November 25th, 2024, Tesla was trading at 345.16, but my estimate for Tesla is 227 or so. A couple months earlier in July 1st, 2024, when silver was 28.48, the actual value for Tesla that day, it was trading at 251.52, and my estimate was about 229. I can draw a line. I can basically plot the graph of these estimate points, which I did in red here. And I can just look at this and see, all right, well, this line isn't doing a great job of modeling this data. I can just see that, right? I wouldn't expect it to. The correlation is only 0.2. There's not a really strong degree of linear relationship between these variables. The line is not doing a great job. That's not surprising. It's the line of best fit, but it's just not a good model. It's the best model we can do with just the sticking to linear models, but it's not a very good model. If I look at Google and Tesla on the other hand, or well, not on the other hand, but if I look at Google and Tesla, things get a little better. I see these are my coefficients, my intercept and my slope. But again, I won't harp on this too much. But we see, again, we get a model that doesn't look great. Again, correlation of 0.35, that's only about a third of the way from 0 to 1. I'm not expecting a really great model to come out of this. Google and PIMCO, well, now we're getting up to a correlation of around 0.8. This is where I'm starting to say, okay, I think that a linear model might actually do a good job here. I think that there is a high degree of linear relationship between these two variables, and a linear model might do a good job of explaining that relationship. And do the same regression, get this same output as before. Not the same exact output, but similar output. I get the intercept and the slope. And I see that this line just visually fits the data a lot nicer than the previous two examples. And if I look at Google and Amazon doing something similar, again, I would run my regression. We'll look at how to get these numbers in just a second here, but I just want to overview what the goal of all of this is. I get this intercept and slope. Excel gives that to me. I plot the line and I see that in this case, just visually, this looks like a very good model. This red line, my model, is staying very close to most of my data points. Or these Amazon estimates are fairly close to the actual values of Amazon for certain Google prices on given days. Okay. So now let's ask, how do I actually generate this table? This thing where we're getting these coefficients from, and then using that to plot to see if visually, just if the model looks like a good model. Well, what I'm going to do here is use my data analysis tool pack. So I go up to data, see where it says like file, home, insert, draw, can go over to data. And then you should have data analysis here. We added this in earlier in the semester. If you don't have it here, I'll show you really quickly how to do it. You go to File, Options, and you should have this screen under File Options. Then go to Add-ins down here near the bottom on the left toolbar. So General Formulas near the bottom is Add-ins. And then down near the bottom over here, we see this drop down, Excel add-ins. Next to that is Go. So we'll just hit Go. And then just make sure your analysis tool pack is checked, hit OK. And then you should see data analysis pop up here. Under the data tab, we hit data analysis. We should have had this back when we discussed things like one variable stats, that kind of thing, and histograms and so on. But just in case you're on a different computer or something. Okay, if we look up and down here, we see lots of different things some things that we maybe recognize more now than we did when we looked at this before for histograms and such. But if I go down, and everything's in alphabetical order. If I go down to regression, hit OK, it brings this up. It says input Y range, my dependent variable, and input X range, my independent variable. So I'll pick Tesla to be my dependent variable. It's the Y value. So I choose Tesla's header as well as all of its data. And then for the X range, I'll pick the silver shares, silver's header all the way down to the end of its data. I did include labels here, so I'll check that box. I included the SLV and TSLA headers so that I know which one's which and when it reports it to me. I'll output in a new worksheet ply. So it's just going to make a new worksheet next to this one for me. And I won't worry about outputting all of this other stuff at the bottom here. Let me hit OK. I'll scale it up to the size you can see. And what I'll do is I'll just click on column A, hold shift and click on column I. And then if I hover between columns I and J, my downward pointing arrow turns into this kind of like two arrows pointing to the side. I'll just double click there, and that will make sure that, from over here, I can't see what half of this stuff says. But this will just automatically expand all the columns so that I can see what they say. And I see that I get these same coefficients as before, the same slope and intercept for my model, the same about 140 for the intercept and about 3.13 for the slope. Right. That was exactly how I got this sheet here and got these coefficients. Let's come over here to VIX and Amazon. Here, VIX is what's called the volatility index. When the market is volatile, when people are trading a lot, buying and selling a lot, the VIX is high, and that tends to happen when the market's kind of crashy, when stocks are doing poorly. We see a correlation between the VIX and Amazon of negative 0.47, a negative relationship. Right, when the market's kind of crashy, stocks tend to not be doing too great, and that's when the volatility is fairly high. The volatility index then is also high. So people will use the VIX as an asset that kind of moves in an opposite direction of some of their stocks, and you can use that to kind of diversify a little bit. You can kind of invest in the VIX, roughly speaking, and then when your stocks do well, the VIX won't do well, and vice versa, and things kind of balance each other out that way. But let's try to do the regression model on VIX and Amazon. So we'll do the same thing. Go to the data tab, data analysis. Regression's already selected, so we'll just hit OK. And let's just get these ranges out of here. my y range, my explanatory variable, or sorry, um, my dependent variable will be Amazon. So I'll click AMZN, hold shift and click at the very bottom of the data. So I've included the label. For my X range, for my explanatory variable, now it's the explanatory variable, will be VIX. This is my independent variable. So I'll click on C1, the VIX label, hold shift and click at the end of the VIX data here at C105. I do have my label selected, so I'll leave that checked. And again, I don't need to output any of this other stuff. So this is VIX and Amazon regression. Let me zoom this in a little bit. And again, I'll do that trick. I'll click on the column header A, hold shift, click on the column header I, and expand my columns. And I see that my intercept is 230, but importantly, my slope is negative 5.06. So for every 1 unit the VIX increases, if VIX goes up by 1 unit, I would expect Amazon share price to go down by $5. They move in opposite directions, roughly speaking. It's a little bit technically incorrect to say it that way when we're talking about increasing or decreasing, but it's close enough for what we need. Okay, so one way we can assess whether a model is a good model is by looking at it. If I just look at the scatter plot with the model, does it seem like the linear model does a good job of staying close to most of the data points? Not at all here, but on something like Google and Amazon, much better. Do we have anything a little bit more objective than that? And yes, we do. There are two things we can look at. One is this value here that's r squared. So you see in column B, row 5, we have this number 0.0432, r squared. What is r squared? R squared is the coefficient of determination. What r squared is it's the percent of variability in the y value, in the y or the dependent variable, explained by variation in x, in the independent variable. In other words, it's the explanatory power of the model. R squared, the coefficient of determination, is literally the correlation coefficient squared. Correlation coefficient times itself, right? 0.2 times 0.2 is 0.04. So it's fairly easy to compute. There's this thing adjusted r squared. That's a different story. We're just looking at the normal r squared. It's easy to compute. And here I look at this r squared and I see 0.04 or 4%. In other words, this model is only explaining 4% of what's going on, and 96% of what's going on is left unexplained. So it doesn't look like a good model. Its explanatory power is terrible. It's not really explaining much at all. We can also set up a hypothesis test. Our question here is, if we build this regression on the basis of sample data, and we get a slope coefficient, this 3.13, that's non-zero, what would a zero slope coefficient be? Well, if this was 0, then my estimate is just like y variable equals number. In other words, there's no dependence whatsoever on the other variable. A slope of 0 would mean no linear relationship at all. And a slope that's non-zero would mean like yes. there's some degree of linear relationship. So we could look at a hypothesis test and basically say, do we think that there's no linear relationship, in which case using a linear model would be kind of silly, or do we think that there is a linear relationship? When can we reject the null in favor of the alternative for a small p-value? So if we see a low p-value for the slope, maybe something like p less than 1%, we can reject the null in favor of the alternative. If I look at my p-value here for the slope, I see it's 3%. I mean, this would be significant at the 5% level, not at the 1% level. But I think that usually in regression, we're looking for something far below 1%. So my R squared is low. A good model would have a high R squared. My p-value is not very low, not very small. A good model would have a very low p-value. And my model just doesn't look good. It doesn't look like it does a good job of modeling the data. I can see that maybe in another example, I might see a pattern that's very clear in the data, but that's not captured with a linear model. So just looking at it and seeing doesn't make sense. So all in all, this silver Tesla model, not a very good model. I wouldn't want to try to explain Tesla stock price using the price of Spider Silver shares. Now, if we jump over to say something a little better, Google and PIMCO, well, here we have a model that looks pretty good. There's a couple of areas where some of the data points are a bit far away, but my correlation of 0.8, yields an R squared of about 0.6. My coefficient of determination is about 60%. In other words, this model is explaining about 60% of what's going on with PIMCO's price using Google's share price, and about 40% is left unexplained. But if I can explain what's happening with a stock, if I can explain 60% of what's happening with a stock with only using one other stock and a simple linear model, it's probably a win. I also see the p-value for the slope. Remember, this e means times 10 to the power. My p-value is 10 to the minus 22. That's about as close to 0 as you're going to get. 10 to the minus 22 is very close to 0. Remember, like 10 to the minus 2 is like 0.01, 1%. 10 to the minus 3 is 1 in 1,000. That's 0.1%. 10 to the minus 22 is very close to 0. So we have a small p-value, relatively high R squared. We have about 60% explanatory power, and the model just looks reasonable. And if we go to something even better, like Google and Amazon, remember the model looks very nice in this case. My R squared is 91%, my coefficient of determination, 91%. I'm explaining about 90-ish% of what's happening with Amazon stock price using Google stock price. So my model is explaining about 90% of what's going on, leaving only 9 or 10% unexplained. And my p-value 10 to the minus 56, right? We're looking for something like 10 to the minus 2, or maybe 10 to the minus 3 as being highly significant. 10 to the minus 56 is a very, very small p-value. And of course, as I mentioned already, the model just looks good. So it looks like a reasonable model. It has a very high R squared, very low p-value for the slope. So I would be happy using this model. Okay. And if we look at the VIX in Amazon, the coefficient of determination about 23%. I'm trying to explain what's happening with Amazon stock price using the VIX. This model is really only explaining maybe a fifth or a quarter of what's going on. Probably not a great model. Not terrible, but not great. My p-value is 10 to the minus 7. That's certainly significant. It's much smaller than 10 to the minus 2. But if I look at, if I try to draw a straight line through here, I don't quite have enough time to build the model and draw the line. But if we imagine drawing a straight line through here, screen cap it and move it over here. It's going to have a negative slope, but maybe something like this. I don't know. I mean, yeah, we have a significant p-value, but I'm only explaining 20-25% of what's going on. This line doesn't really look like it stays close to most of the data. I also see that there's the data on the left side here are much more nicely clustered around the line, but the data on the right side over here are much more diffuse. I might look and see this pattern and say we're not capturing anything about that pattern at all. I would be, hesitant to use this model. If this is the best I had, it's not maybe terrible, but I certainly wouldn't say that it's a very good model. So how do we decide if the best linear model is good? We look at the picture. Does it seem like the line stays pretty close to most of the data points, that I don't see really systematic deviations? I look for a high R squared, a high coefficient of determination, a high explanatory power for the model. Is this number 70, 80, 90%, or is it like 10, 20, 30%? Is it not explaining very much? And at the bare minimum, I want a low p-value for the slope. I want statistical significance for the linear relationship between the two variables in the first place. If I'm looking to model that relationship, I really should at the very least be somewhat certain that that relationship exists. Okay, so that is our discussion on correlation regression. Again, I know that was probably kind of a whirlwind discussion and a lot of material very quickly, but we're not looking to be experts in this material, really just to kind of scratch the surface to understand some of the main ideas and to have been exposed to it once if it comes up in the future. So, you could spend easily an entire whole course or multiple courses on this material. So we're certainly not covering it exhaustively, but if you understand the high points from today's lecture, I think you will be good for the exam and for the homework. All right, let me stop the recording.